Well, a reminder for anyone that wasn't here for the first session, I am recording this. I am only recording my mic and the slideshow, so I'll try to repeat questions and whatnot for review, but you will not be in the recording, so you don't have to worry about things you say being accidentally leaked. So, welcome to LabVIEW Advanced Workshop for 2019, or what was going to be building a robust autonomous. I don't know if you watched the Kickoff video or not, but we don't need autonomous anymore. Yeah. But I do think that during the sandstorm and my basic reasoning for why you want to code your robot so it can behave well for on its own or handle sections on its own that you will do well. I have an example of how a 80% consistent autonomous in past years would actually put you ahead of a 100% endgame. That doesn't apply this year, but I am going to say that during the sandstorm, the more your robot's able to help you, the less frustrated your drivers will be, and the more you'll be scoring. So I'm going to touch on these things that I think you need, and I'm actually going to skip the easy to edit portion. That was using a file-based setup entirely for autonomous and changing how the autonomous API works. I was digging through the rules, and I'm not real clear on whether we're going to use the autonomous API at all. Not sure if we are or not. Even if we are, I think the coding is going to change drastically, so I'm going to skip that section. I'm going to go into sensors that you can use and how to use them, and then I'm going to do some examples. I've actually got a RoboRio here, and I can do the vision examples. I can do some vision examples on using the vision targets. I was playing with that already this morning. Also, quick note, for a robot to succeed in any game, it needs quick and effective mechanisms. I'm not going to go into those in this presentation, but felt like it was necessary to acknowledge that that is part of what we are doing. Even as software and electrical, we need to be making sure that our mechanisms are what we need them to be. Okay, so when you're dealing with sensors and trying to use them for things, you oftentimes wind up with something called closed loop control. An example of that open loop is you have an input reference, say a joystick button or a joystick value, that goes to your controller, which in our case is the teleop VI, and that affects something, maybe a motor controller, and that creates an output, the speed of the motor. And I push a button that says to turn the motor on. Did it turn the motor on? I don't know. Closed loop is when I take something, a way of measuring that output and bring it back to the initial input. And there's this nice little add symbol for people who study control theory, but in more practical example, I want to move the arm, which means I'm going to input a joystick to teleop.vi. Teleop's going to decide to set the motor to 0.25. And if I put a potentiometer on the end of that, I'm now able to tell when that changed. And the way we would diagram that is by piping that potentiometer back into teleop. So teleop's reading that potentiometer and knowing what the arm actually did. PID is a way of doing this. It stands for proportional integral derivative. And what you do with PID control is you take the error of time, t being the current time, or the error being how far off you are. So basically just how far you're currently off from where you want to be. The proportional part is you multiply that, how far you're currently off, by a constant. The integral part is that you're going to take the integral of the error over time and multiply that by a constant, and the derivative part is you can take the integral of the derivative of the error. More to come on why you would use that and everything. For the proportional, it's a constant multiplied by the offset, or the error. The larger this is, the faster the robot approaches the set point. I'm referring to the constant here. So if I have the robot sitting at 90 degrees to the field, and I'm going to use the gyro as my target, and I pass into my PID a proportional gain of 1 that will output a value to my motor of 1, which is full speed. So it's going to turn full speed towards the to make that 90 degree turn. Well, that might be really fast for a 90 degree turn. Maybe I want half speed. Well, 0.5 at 90 degrees, that's 1/45, whatever that decimal is, would be the constant I want it to start at half speed and slow down as it approaches the target. That will help me to not overshoot the target all the time. The integral part is a constant multiplied by the integral of all previous errors. The larger this is, the less the overshoot and settling time. In other words, with proportional alone, you can overshoot and bounce back and do that a couple times. You want to get the proportional portion to where you consistently overshoot a little bit. And then you can use the integral to account for the fact that you've been off for a while, so slow down the approach. But if the integral is too large, the integral constant, then it will eventually react violently to any error. If you think about it, if I am at say a gyro reading of 1 degree and I want to be at 0, eventually long enough and exponentially so that integral is approaching infinity, and as it approaches infinity, all of a sudden I'm moving very fast and overshooting, and I maybe spin 3 circles and I'm sitting there for a really long time and then spin 3 circles the other way. The differential part, the larger this is, the less the overshoot and settling time. I'm sorry, I didn't update those slides correctly. The integral is to eliminate steady state error. That's how far off you settle. Differential is for the overshoot and settling time. If you download the slides or the PDF version of the slides, I've got references to several articles on these on PID and how it works that are very good, and I've been referencing them over the years. Any control system, you have to tune it. There are several methods, public shared methods on how to tune a PID. These are just some that I have found over the years. I've primarily used either the Ziegler-Nichols or the manual tuning, which isn't really a method so much as a step-by-step. Again, if you download the slides or the PDF for these slides from the workshops.frclivetutorials.com, I have PDFs and YouTube video links for all of these tuning methods. So some example code on what this might look like. I'm going to take the desired angle, I'm going to take the angle I'm currently at from the gyro, and I'm going to pass that into the desired is my set point, the current is my process variable, that's the terminology. My output I set to -1 to 1. Here in a minute I will actually code this up to show all the people who aren't familiar with this just yet what it looks like to do it. And then my PID constants, 1, 0, 1, and 0. This is saying that I want, this might be a little high of a p-value, very likely 0.75 is sufficient. And 0.01 is oftentimes what I wind up with for a drive straight on my integral. And that is actually what this winds up being. It's the angle I want to be going at versus the angle I'm actually going at. Make me go at the correct angle at this speed into my arcade drive. So that makes me drive straight very efficiently. You can also use this for turning to a specific angle by setting the desired speed to 0, but it oftentimes requires different gains. And that's what we call the constants, is we call them the gains. So I've talked about how to use the sensors, and I skipped how to make this easy to edit. And I'm going to talk about some different sensors for making your robot be consistent, regardless of the field, the setup, game pieces, battery level, whether or not your driver can see what it's doing. And one of those sensors is the encoder. There are lots of optical encoders as well as other types available out there on the market. Some from AndyMarks. There are optical encoders on just about every maker site, including Amazon. I know Breakaway has tended towards some really good optical encoders from US Digital. Might speak with Brian Jones about how to get those. Places to use encoders when trying. You should use these when you're trying to measure rotational speed, because they're able to detect multiple rotations and measure the rate at which the events in the encoder are occurring. Also, when trying to measure rotational distance greater than 8 rotation. I'm saying 8 because the alternative to an encoder is a potentiometer, and the maximum number of turns that I know of a potentiometer being rated for is 10. And so I'm giving you a little bit of a margin there, saying, okay, well, we'll probably do 9 or 10. We'll get an encoder for that so you don't break your potentiometer. But if it's going to be less than 8 all the time, use a potentiometer, and I'll explain some more on that later. Also, encoders are good when you don't care about the starting position, because they're that's how they work. They work by counting up or down depending on rotation. If they are an absolute encoder, if they're an incremental encoder, they always count up. They don't care about starting position. They always start at 0, regardless of where the arm is or where the elevator is, whatever you have it measuring. Examples that this is good for using are on the drivetrain. You want it to start at 0 in that case, because that is your 0th position, and that's going to travel more than 8 rotations in a match. Also, let's say we would do a wheeled shooter, which I don't know if we would be using this year, but you might do a wheel intake. So if you're trying to measure the speed on that, it's going to spin more than 8 rotations in a match usually, and you care more about speed than you about the exact rotation. You also don't care about where it's starting, because whether it starts rotated up or rotated down shouldn't matter. And then this is an example of the code for an encoder. So much like the motors I did in the first session, I've got a case-sensitive name going into my dev-ref get. And then I get the encoder value, and I'm able to get either the distance or the rate, or both. The rate being how fast it's going, and the distance how far it has gone since last reset, or power up if reset has not occurred. Reset is another VI that I can call on an encoder. And so to make the control on an encoder, I might read that encoder and pass that value into the PID process variable, and my set point is some speed, and I set the motor output to that value. I'm actually going to jump over to LabVIEW and show you this one, because thinking about it, I don't think I've got much of a that's not going to work. Control C. Okay, so this is a snipping. So it is a picture. It's got this little icon at the top, which tells me that this should work. What I'm going to do is I'm going to go to my desktop, and I'm bringing this up because I can't get to the desktop with that. Okay, there we go. Copy this to my desktop. If that's going to work, please. Let's save this as a picture then. Yeah, sure, save as picture 1. The tutorials website, as well as frequently on Chief Delphi, you'll see instances of this. So it's a picture. I can open it up. I can view it. Web browsers know how to render it. But I can also drag it into LabVIEW, and that should have become code again. I'm not sure why that didn't. I know why that didn't. PowerPoint messed with it. Do I have it? Okay, I'm just going to do it by hand. So actually I have the PID VI here. And if I go to the robotics library under sensors, that's where I can get to the encoder stuff. I'm going to do the ref num get. Also, if I right click, I can get the encoder palette pretty easily. And I want to get the encoder value. And just by sticking it near it, it auto-wired up those two values. Nice and neat for me. So create a constant on this. This is arm angle. Again, those are case sensitive. So I've got the arm angle, and I want the I want to do a control on it, and the yeah, I'm going to do the distance because this is the angle. That is my process variable. My set point, I'm actually going to use a index off of my joystick, and then the output I'm going to take to a motor. I'm going to replace reading directly from the joystick from that. I'm going to pipe this here. So that now instead of setting the motor speed to whatever the joystick was, now I'm setting it to have the arm position match where the joystick is at. The PID by default, the output, if I create a constant here, ranges from -100 to 100, so you always want to change this. There are some other options. I personally believe that this is the simplest option, is to just set the range. Also, on the gains, I want to set that up. Ordinarily, you want to create a control, and if you double click on that, it takes you to the front panel, and you can adjust these while running. The only hiccup with that is once you've got it tweaked to what you would need it to be, A, click out of the box to make it apply, but B, you'll need to go to data operations, make current values default, or do that under the edit menu to make these values save as being part of the VI. So just go ahead and do that, and notice that that was a change as well, and now I can save it, and if I can reopen the VI, and that is there again, same values. Just curious. Nope, it didn't. Okay. So that's an example of using the encoder for a control of an arm angle or of a shutter speed. Potentiometers, use these when you're trying to measure rotational distance less than 8 rotations, so they're actually better at arm angles than encoders are, because your arm may travel 170 degrees maybe. And you do this when you care about the starting position or absolute positions. So I want 0 to mean on the ground regardless of when I turned on the robot. If I use an encoder, 0 is wherever I turned on the robot, or wherever I run the reset VI, which you can do through a button or something on the joystick. Versus the potentiometers, they're that angle, period. And that makes them work a lot better for things like arm angles and elevators. They do have the hiccup of if I'm getting ahead of myself again. The control algorithm looks very similar. The only difference is that your read potentiometer is between 0 and 1, so now my set point is some value, and I've commented here that that means to put the arm at 90 degrees. So I'm setting my set point, and I'm controlling my motor output. Same setup as with the encoder. There is an easy way to make a potentiometer relative to a known point. I'm not going to go into a whole lot of that here. You can go to my website and look at the potentiometer tutorial for how to do that using a file-based set point. The next sensor that we've normally needed, and honestly this year I think we're going to need it a lot for the sandstorm and to make drive straight, make it easy for your robot to drive straight, to help align on things. But it's the gyro. I don't think turning to specific angles is going to be as much of a thing in this year's game. It can be. For some reason, my coders on the team I'm currently working with really thought the drivers were going to want it. Drivers never used that last year. But again, very similar. I can do the gyro, get the angle, and pipe it into a PID value. I've got 2 examples here, one using the gyro from the WFI library, which is able to handle an SPI SPI bus gyro or AI2C gyro like you can buy from AndyMark. There's also the NavX gyro, well, IMU, which is significantly better and doesn't drift as much over time, meaning it just sits there and kind of counts up. It doesn't do that as much, and but it's also very expensive. By Cowie Labs, every time I've gone to look for it on AndyMark, they've been sold out. That tells you how popular this thing is. They have their own API, but again, I can get the yaw, which is left-right rotation, and pipe it in, and this is effectively the same. The only difference is I've got a constant desired angle versus a control. And then vision, I actually added this one in as a result of watching the video this morning and looking at stuff, I think one of the things that we're going to want a lot of this year is things like an auto approach or auto lineup, because you're trying to line up on a target that's not going to be from the driver straight going away, which is the easiest to line up on. In fact, none of the targets you're going to line up this year are like that. And by targets, I'm talking about areas where you want to put either get a game piece or drop off a game piece. But the only thing that's going to be easy to do by line of sight, in my opinion, is going to be getting on the ramp for the end. So I'm actually going to jump back over to LabVIEW, and I'm going to close out of the Kickoff project, and yeah, we can disconnect from the RoboRio. Yeah, save all. And I'll bring this back up at the end too. That is my email and phone number. You are free to reach out to me whenever you want, or whenever you need to, I should say. So if you go to tutorials and nope, utilities. Okay, come on, where is it? I need to get to the examples, and I don't want one of their built-in tutorials. I want to actually open. I want to find an example. And I'm trying to remember where it is. I don't know why this is so hard to listen. Find examples. There it is. Thunder help find examples. Last year, the vision code that was shipping was highly lacking. I was slightly disappointed. This year, it is there again. I can go to the FRC Robotics RoboRio, and there's a vision example. There's also several other examples in here that my fellow mentors actually work on writing, and they rely heavily on for coaching our kids. And I have actually seen at least several of them figure a bunch of stuff out by, okay, I'm trying to set a joystick, and go look at the joystick. At any rate, for this year, 2019 vision example, it's around the retroreflective tape that's going to be above the on both the ship and the rocket, the hole where you can put the. I am losing words really quickly right now. The game pieces. That's not what I wanted. Double click. There we go. No. Okay, come on, open up. What am I missing here? Oh, it did open. Okay. So one thing that's nice about this is actually a default LabVIEW project, or default robot project with a more set up vision processing. Okay, it's not the default; it is the bare minimum. With a setup vision processing VI that actually can take in an image from a camera and shows you what is the result of the processing. I'm actually going to step away from this, and I'm going to use the desktop example. That is, no, I don't want to view it. And this allows me to run example code on the desktop. In terms of the controls and what I get out of it, it's the same. It's just that I'm going to use, I can use my webcam, in theory. See if I run a config shown. It's not getting it. Probably because my webcam's busy showing you guys stuff. But I can go and I can use these saved images to try to process examples and see what it takes to set it up to detect these vision targets. And so this is an example. Okay, so I've got some sort of a green light LED ring around my camera, and so it's causing the. Why did that close? I had my notes open and they just decided to close on me. So it's kind of green, but notice I'm not really detecting very much of them. So one thing I can do is I can shift the saturation. That's giving me more of it, but not really helping very much. Versus I can bring the value down. Again, not really helping very much. That helps in the wrong way, which tells me that actually what it's seeing, what I'm what I'm detecting and applying in the mask isn't the color that I really want. That's more of a bluish green than it is a pure green. So I'm going to shift this way. Okay, so that was a little hard to tell because of all the extra noise, but I did see those get fairly solid, and if I bring this down, that's more and more well-defined. Oop, too much. Okay, so that's a pretty well-defined shape. It's able to detect the target. I can shift this to help me fill in the shape better. This is acceptance bounds is what it is, and this code has already been set up to detect the vision targets, and based on the camera type, and I'll go more into that, but the different cameras have different resolutions. Based on the camera type, it's able to give me the distance to that. How well it scores is mostly dealing with how well it is able to detect the object. I got a 97 and a 90, so for this image, this is a very good setup. Now I'm able to know where the center is in pixels or in a normalized value where come on, give me, okay. Results of the image processing, including the distance, center, and bounds. Yeah, that's really terribly descriptive. The center, in the past, that's been -1 to 1 bounded. I'm a little surprised that that's not right now. But I'm able to use this is an X and a Y, to guide my robot using the X variable as my processing variable to drive straight towards it. Breakaway actually used this with First Stronghold to align and shoot into the tower in Autonomous, and it worked very well, at least in practice. I was not able to watch the matches, so I don't know how much they used it in the matches. One thing I should note, all of these values, now I've got my filter tuned. I want to go ahead and stop the VI. I want to right click on this cluster group, and I want to go data operations and make current values default. That way they are saved. And I can reload this, and this comes back to this value. That's also what makes it, if you deploy this to the robot and run it, that's the default value that we'll use there. So I can run again, and I've got some values. I can try different images, and it's like that could pick up. This is actually set up, the mask that is set up is only set up to detect the targets. So again, this picked up very well. Thinks it's 2.5 feet away. Couple more targets. This one's blocked partially by a disk, but I'm still able to detect it, and I'm able to detect that one. And so there's a bunch of different example images of things you can try. In the event of having a working camera, it's a little weird that it didn't. Okay, so it's reading the camera on load. I think this was USB 0. There we go. Okay, so you can see my camera. You can use this. It's plugged into my PC. But you can use this. It's running the same code that the RoboRio would be running. If I had retroreflective tape, I'd be holding it up here and seeing how it tracked and stuff like that. But we can switch back to using the images. And yeah, cool. So that's a nice example, and we can use it to help line up and go straight into a drop zone. We can just call it that, to drop off the hatch covers or the cargo. And go ahead and stop. This is an example project, and it doesn't contain all your stuff, but what happens is the vision processing.vi, if you move that into your main project, which if I were to open up another project and open that back up, so here's my project, and I click on the project file to open the whole thing, and I'm not seeing it. Up there it is. It's LVP now, so that's different. I can open this up and I go to robot main, and by default there is a vision, there actually is not. This is just sending it to the PC. Okay, so they've really actually separated this out now. Okay, so all I would have to do is drop the, go back to the Vision example main. I would drop this Vision VI into the other project, and it's saying, oh, hey, here's another one. Do you really want to add it? And I'm going to say, yes, I want to add it and all the dependencies. Good. Yeah, let's save all. Okay. That should have worked. Let's go this way. Select the VI. Let's go through my documents. This isn't saved, that's why it didn't work. I've got properties, I can see where this is at. Okay, open it up. And go properties. I should be able to see where it's at. It's in LabVIEW program files examples. So what I should do is make a copy of that is not there, but rather in my project under my source control. Not National Instruments, but LabVIEW data. And okay, we're going to skip. We're going to rename the other one a different name. And paste. So now if I reload my okay, it's whining about a few things, all of which should solve if I open this. It's asked me which one to use. I think that was Slack. Okay, I can ignore that. It's asked me which one to use. I want to use this one. And I want to use my Kickoff version. Yep. 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 There we go. So now I can open it up. I'm still broken because the global VI that I was trying, this is not quite going as well as I had hoped. So it's trying to pipe the results into here that does not exist in this version of the robot global data, but I can create one by going here and copying this and going here and pasting it. And so now that does exist and everything's happy and nice. What that means then is this is running in a loop on its own, and in say autonomous, yeah, save that. In my, I'm going to go to TeleOp actually. I can select a VI. I can go select that global data VI, which is a it is a global variable. One thing to keep in mind with LabVIEW is to only write to these in exactly one place. It's fine for this scenario because I am piping it. I'm giving it data in. That didn't do what I wanted to do. I wanted the global. There. There. Now I can change this to a read, and then I can select the result. And maybe I should rename that vision result. But now I'm able to see, to use in TeleOp the results of the vision processing. It's okay to have a global if you only write to it one place. You can read from it in multiple places. You should. I'm going to refer you to FRC LabViewTutorials.com. /tutorials/FDV, which stands for Functional Global Variable. That is a particular tutorial on when to use different types of variables, and in particular how to make the FGV work and why you would want to use it. And that is what you should use if you need to communicate between different threads. That's the reason the global is there. TeleOp's in a thread and Vision's in a thread, and so I'm communicating between the two different ones using the variable. FGVs allow you to communicate between different threads and can prevent issues with race conditions where you have multiple writes going on, but they aren't as performant as just a straight up global. So go there, read the tutorials on why you would want to use different ones. Back to the PowerPoint. There are other sensors available. I actually just added the camera in this morning because of how important I think vision is going to be this year. For using the Allen Bradley light sensors to track a line, they are a digital input that just says I see the line or I don't, and you should go to the white paper that's published on those. You just Google FRC line tracking white paper and that should pull it up. It's very good on different methods and how well they work. It's also written for LabVIEW, so the code there is directly applicable. This tutorial that's up there and published is for using an Arduino connected to your driver station to provide extra inputs and outputs. So you can code the dashboard program to maybe when the robot thinks it's lined up, the Arduino turns a digital output on, and if you wire that up to some LEDs, that tells your drivers via the LEDs when it's lined up and when it's not, which can be very handy. How we're doing on time? That was 35 minutes. So my last two topics are demo and questions. I'm going to give you an opportunity to ask any questions you want right now. The demo I'm planning to do is a theoretical architecture for a robot that does an auto lineup during the sandstorm. No questions? Okay. So jumping back over here. So I've already set up my it's whining about a few things. Why are you in conflict? So I can resolve this by specifying which one I want you to use, which is that one. And this one, but this is not the one that's in the file, that's why it's whining. Okay. I'm going to start, I'm going to undo that vision thing by deleting this one and renaming this back to just that. And then if I open up the project now, there shouldn't be any conflicts. I can still thinks that's in conflict. Let's remove this actually, because that's the okay, all conflicts gone. I'm going to open up the existing vision processing, and it doesn't do anything. Okay, so I want to replace this with the stuff from the other VI. Which is the cleaner way to do this. And if I can figure out where that was. Let's open up another project. There we go. The only one I'm going to want is this guy, so I'm going to go to properties on it. Or not, just open it up. And notice I went to the vision processing rather than the desktop example too, so it's not doing the file-based thing, rather it's give me the camera. And there's some setup here as to which camera to use. If you're using a USB camera, set this to true. If you're trying to use an IP camera, this might work, or you might need to put an actual IP address in. But this code in here is the code that I want to move to this version. Which all he is doing is nothing. This is all empty. So I'm going to delete this, and I'm going to go to this version. I'm going to highlight and copy everything. Delete that too, and paste it in here. And it put it in here, but everything's broken. Come on, put it in the while loop. Okay, that's the iMac. That is the camera. Oh, I missed a couple of things. Or did I? I have a weird wire thing going on. Pipe through that into that. Okay. I also want this color control. So that's going to go. Okay. So the color actually goes here. Maybe I should have done this by replacing the whole VI. At this point, I'm almost done. This goes here. This goes here. Control U to clean up the diagram. Control Z because I don't like how that looks. Control B to delete broken wires. I still have a broken wire here for the pixel measurements. And I'm going to create that and drop it here. And wire it in. Come on. There we go. So if I open this up, this is actually something I meant to mention earlier. This is doing a bunch of magic on some different stuff, and that's not the VI I meant to look at. The VI I meant to look at is the one that takes, not you. Is the one that determines the distance. And this is I was looking at it, it's a fairly well documented VI. Has the image come in, and it's going to do some math on it. It determines from the camera type what the field of view is vertically, and it divides that by 2 and does some different stuff. Explanation down here on how to measure this using some like strips of tape on the wall and a camera. And then you may want to add view angles. You can add an additional row here and a row here that will then correspond to this new camera type, which you would have to open the type def and add it to the list. Not like that. Edit items. Or rather than editing all of that code, camera type So this is just getting the camera view angle and the point of field of view. I can disable this, and I can pass out the value for my camera, which might be like 960 or something like that. At any rate, chances are good though that the camera that you're using will be in here, especially since they have both of the Microsoft live camera models in here, as well as the old network camera from D-Link. Don't say that. Okay, so there's that. So now I've got my Vision VI. It's still broken. Why is it still broken? This shift register is unwired. So this is an example where I want to add some white space in. I can see the missing wire, connect it up. Now I'm able to run. Cool. Save that. My Vision VI is able to write and push the data to my teleop. And in teleop, how are we doing on time? We got, okay. Probably went into more detail on how to set up the vision than I intended to. I'm going to use my second joystick, and I'm going to say when I push a button, let's say button 0, which is the trigger on flight style joysticks. I think it's the upper left thumb on the Xbox and PS3 controllers. While that is active, rather than taking these values and piping them into Arcade, I'm going to put a case structure around them and say that while this button is pressed, that would be the true case. So actually I'm going to swap this, make this the case, false case. So in the true case, I'm going to do some stuff with my vision to help it drive straight on the target based on the camera. In the false case, when I'm not pressing the button, directly read the joysticks. I wanted to do that this way. There we go. So if I'm going to drive straight onto the target, that's probably using the vision to decide the angle, but I want to drive at the speed that I'm telling it. So I'm going to grab the index 1 anyways. So I'm going to bring this over here to the true case. So I'm still grabbing my throttle from the other joystick, but my angles can be determined based on, I apparently got rid of that, data. Select a VI, go to global data, drop it in, change this to read, and I want the result. Result's not a good name. I'm going to open this up. I'm going to rename it to vision targets, so that when I'm looking at this next week, I know what I'm talking about. And I have to change this to being vision targets. Also, why are you broken? It's broken because I should have connected out to something if I'm going to read it. It's also broken because of the missing tunnel here. It's open because it's unwired. So also in vision, that's going to be broken as well, because that now doesn't know what result is. But if I change that to vision targets, then vision is now fine. So I can close back out of vision. Yeah, sure. So I'm going to take my vision targets, and if there is one, ooh, okay, so if there isn't one, I probably shouldn't move, right? So I'm going to do a select, and I'm going to use, this is an array of the targets, so I'm going to use an array size to know how many there are. Why is that whining? Ah, that's not an array, that's the best one. Okay. That's fine. I probably only want the best one. So let's rename it to vision target and do the same in vision. There's a certain nuance to doing live demos, right? So I actually don't need to index the array because they just have the best scoring target as is. If I unbundle by name, that will give me the values that are in there by their name. I can get the distance, I can get the score, I don't really care about that. The normalized center, or if I go into the rectangle, I can get 4 different values. Also, similarly with the pixels. The center is actually a cluster, and that cluster I can also unbundle by name. What am I missing here? Here's where context help is helpful. Yeah, it's a cluster, but I can't unbundle my name. Apparently I can, but they don't have names. Okay. That's nice. Well, rather than grabbing the center, I'm going to grab the first value, which should be the x. And if I don't have one, that's going to be 0. So I need a way of knowing if I have one or not, because I don't want to move if I don't have one. So in vision processing, going to change that again. Yep. I'm going to add a Boolean indicator. How are we doing on time? 250. Supposed to be done at 3. What time are we supposed to be done by?
3:30.
Okay. I think we have enough time. Here I'm going to do array size on all of the targets. That is actually way over here. Should be getting all of the targets here. Or is it just going to give me the best one? This one's only going to give me the best one. So I'm going to go off of the score. I'm going to say if the score is greater than 50, then I have a target. So I'm just going to do a comparison. And that's the score, that's the distance, that's the score. So the score greater than 50 means that I have some target. And I'm going to pipe that into an additional thing in the vision target in the robot global data that says has a target. Okay, so if I have a score of at least 50, then I must have a target, otherwise I don't. So then in here, that gives me the target, but I only care about it if I have one. So has target, that goes into here. In the case where I don't, I'm not going to move while that button is pressed. So I'm going to replace that value with a 0 if I don't have a target. So that's actually in the false case. If I do have a target, then I'll pass the index out. So that's the speed I'm going to travel at. As far as steering, I'm going to just use a PID that says I want that center to be 0 because I want to be centered on the thing. You'll probably have to experiment with that for your robot and the camera placement, if that's true or not. Vision target can move up here, this can move up here, move this over here. My output range is again 1 to -1 because I can't do more than a fast full speed spin. My gains I'll have to mess with. Very likely that is going to be too low. I'll just say it at that and leave it there, and that's going to be my X output to the arcade drive. So now I've got if I'm lined up directly, then drive straight, otherwise turn towards it while the trigger on my second joystick is pressed. So that's an example. We've got 8 minutes left. I think I'm going to leave it at that. I've got examples in the PowerPoints of most of the other sensors except for the line following, and I have not updated code on that since the white paper originally came out. So with that, are there any questions?